I want you to try something for me. Just for a second, close your eyes. Now imagine you're standing on a busy street corner in New York City. Keep them closed. What's happening?
Well, I'm hearing traffic,
Okay.
honking, maybe a siren in the distance.
Right. Now open your eyes.
Yeah.
Suddenly, you aren't just hearing noise. You're seeing the yellow taxis, the scheme coming from a vent, the flashing "don't walk" sign. You feel the vibration of a subway passing underneath. You smell the hot dog cart.
Right.
And here's the kicker. You aren't processing these as, like, 5 different spreadsheets of data, are you?
No, definitely not. It's instantaneous. It's a single unified experience of being in New York.
Exactly. That is human perception. It is inherently multimodal. We grab data from every sense and just blend it into one reality. But here's the thing that really gets me. For the last 50 years, artificial intelligence didn't work like that at all.
Not even close. AI was essentially an expert with blinders on. You had computer vision models that could stare at photos all day but couldn't read a single word. Then you had language models that could write poetry but had absolutely no idea what a sunset looked like. They just stayed in their lanes.
Until recently.
Until recently. Now the walls are coming down. We're seeing this massive explosion of multimodal machine learning. We've got robots that can navigate by sight and touch. We've got systems like GPT-4 that can analyze a graph you literally sketch on a napkin.
It feels like science fiction is becoming science fact. But, and there is always a but, when a field moves this fast, it gets messy. Everyone's building cool demos, but it feels like no one agrees on the rules.
That's the Wild West phase of technology. And that is why we're here today. We are doing a deep dive into a paper that acts like a sheriff coming into town.
Okay.
It's titled Foundations and Trends in Multimodal Machine Learning by Paul Pouliang, Amir Zadeh, and Louis-Philippe Morency from CMU.
And these guys aren't just showing off cool gadgets. They're trying to write the physics textbook for this stuff. They're asking, how do we actually build a unified theory for how machines learn from multiple senses?
It's a heavyweight paper. And they break it down into a really specific framework. 3 foundational principles, basically the nature of the data, and then 6 core technical challenges, the how do we build it part.
So that's our mission for this deep dive. We're going to unpack that framework. We want to move past the wow factor of a talking robot and actually understand the engineering reality under the hood.
Let's do it.
First off, we need to define our terms. The paper talks about modality. To me, that sounds like a setting on a washing machine. What does it mean in this context?
In the simplest terms, a modality is just the way something is perceived or expressed. But the authors make a really important distinction here. They talk about raw modalities versus abstract modalities.
Okay, raw sounds straightforward. That's the data straight from the sensor.
Exactly. The audio wave recorded by a microphone or the grid of pixels from a camera, that's raw. But abstract is where it gets really endearing. Let's say you're analyzing a voice recording. The sound waves are the raw modality. But the sentiment, whether the speaker is angry or happy, that is also treated as a modality.
Wait, so an emotion can be a modality?
In this framework, yes, because it's a distinct layer of information. Even the category of an object like knowing a shape is a cat, that's an abstract modality. The whole goal of multimodal AI isn't just to stack these things up. It's to reason across them, to connect the raw pixel of the cat to the abstract concept of pet.
That makes sense. It's moving from data to meaning. But this is where we hit the first major hurdle. The authors lay out 3 principles of the data itself, and the first one. It sounds like a nightmare for engineers. Heterogeneity.
Oh yeah, the apples and oranges problem. Or maybe more like apples and chainsaws.
That bad?
Well, it's tricky. The principle of heterogeneity is basically saying that information from different modalities doesn't just look different, it behaves mathematically differently, it has different structures, different qualities.
The paper mentions a spectrum here.
Right. Think about it this way. If I hand you 2 photos of the same room from different cameras, those are homogeneous. They speak the same language, pixels, RGB values, spatial layouts. But if I hand you a photo of a room and a poem describing the room,
Totally different.
highly heterogeneous. And the paper breaks down why using 3 dimensions: structure, distribution, and noise.
Let's double click on structure.
Okay, so an image is spatial. It exists in 2D space. You move a pixel to the left, it changes the whole picture. But language is temporal. It flows linearly, through time. You can't just overlay a sentence on a photo and expect them to line up.
One's a map, the other's a timeline.
Exactly. And then you have distribution. I saw that they mentioned Zipf's law here. I remember that from linguistics class. The idea that some words, like the or and, appear constantly while hippopotamus is rare. Precisely. Language follows Zipf's law heavily. It's sparse. But pixel data, Doesn't really follow that rule. Pixel intensity is dense and continuous. So if you try to use the same math to analyze a sentence that you use for a photo, the model just breaks. It's expecting a hippopotamus, and it gets a sea of blue sky.
And then there's noise.
This is the one that trips up self-driving cars. Noise looks different everywhere. In an image, noise might be an occlusion, a tree branch blocking a stop sign. In audio, it's the sound of wind. In text, it's a simple typo.
So if you're building an AI, you can't just have a single remove noise button. You need to teach it that a missing piece looks completely different depending on which sense it's using.
Precisely. So that's principle 1. The data is fundamentally different. But that leads us to principle 2, which is sort of the silver lining. Connections.
The shared DNA.
Right. Even though the math is different, these modalities are often describing the same underlying reality. Principle 2 says there's a tether between them.
How does the machine find that tether?
2 main ways. First, statistical connection, co-occurrence. If the visual data shows a dark cloud, the audio data often shows the sound of thunder. The machine learns, hey, these 2 patterns tend to show up to the party together.
Correlation.
Yeah, essentially. But the stronger one is semantic correspondence. We call this grounding. This is where the machine learns that the specific word dog corresponds to that specific fuzzy cluster of pixels. It's not just that they happen together, it's that they mean the same thing.
That feels like the bridge between the apples and chainsaws. They both describe the same world.
Exactly. So we have heterogeneity, they are different, and connections, they are related. That brings us to principle 3, interactions.
This one sounds a bit like connections, but I get the feeling it's more active.
Spot on. Interaction is where the magic happens. And the paper distinguishes this from connections. Connections exist in the data, sitting on the hard drive. Interactions happen when the AI actually processes that data to solve a problem.
So interaction is the outcome.
It's the result of the combination.
Yeah.
And the authors identify a few types. You have redundancy. The image shows a stop sign. The text says S-P. That increases the AI's confidence. Then you have enhancement. Maybe the image is blurry, but the audio is clear, so the audio enhances the understanding of the image.
But then there's emergence.
Yes,
No.
Emergence. This is when the combination of modalities creates an insight that exists in neither of them individually.
Give me an example of that.
Okay, think about sarcasm. Imagine a video of a man falling into a mud puddle. The visual modality is man falling. Now imagine the audio says, well, that was graceful.
Okay, I see where this is going.
If you only analyze the video, you just see a clumsy event. If you only analyze the audio text, you hear a compliment. But when you process them together, an entirely new concept emerges. Irony. The machine understands something that wasn't explicitly stated in either source.
That is fascinating. That's a 1 + 1 = 3 effect.
Exactly. And getting machines to catch that nuance is the holy grail.
So those are the physics. Heterogeneity, connections, interactions. Now, the authors pivot to the practical side, the taxonomy of the 6 core technical challenges. This is basically the to-do list for every engineer in Silicon Valley right now.
It really is. It's a roadmap. Let's walk through them.
Challenge number 1, representation. To me, this sounds like translation.
It is. It's the question of how do I summarize this messy multimodal data into a format the computer can essentially think in? The authors break this down into fusion and fission.
Fusion sounds like nuclear physics. Is it just jamming the data together?
Ideally, it's more elegant than that. Fusion is about integrating the information. But how? Do you just add the numbers together, multiply them? The paper gets technical here, talking about tensors.
I saw the tensor of products. Why does that matter?
Without getting too bogged down in the math, think of a tensor as this massive grid that captures every possible interaction between every data point. So if you have video and audio, a tensor product doesn't just stack them. It looks at how every single pixel relates to every single sound wave. It creates an incredibly rich representation.
But I assume that's expensive.
Computationally, it's a beast.
Yeah.
It scales exponentially. If you have a lot of data, a full tensor product will just melt your GPU. So a huge part of modern research is finding ways to approximate that power without the cost.
And fission is the opposite.
Right. Sometimes you don't want to blend everything. Fission is about keeping things distinct, creating disjoint representations. Think about medical diagnosis. You might want the AI to keep the patient's X-ray data separate from their verbal history for a moment to analyze them independently before combining them. It preserves the internal structure.
Okay, so that's getting the data into the system. Challenge number 2 is alignment. This feels like the matching game.
It is, and it's arguably the hardest part. Alignment is identifying connections between specific elements. This word connects to this part of the image.
Why is that so hard?
Because it's almost never one-to-one. Maybe you have a sentence with 10 words describing a picture with 3 objects, which words go where, or, think about video.
The paper mentions continuous alignment for video.
Right. Imagine you were trying to sync a dubbed movie where the lips don't match the words, the timing is off, the AI has to perform warping, it literally stretches or compresses the time signal of the audio to try and match the visual events in the video.
That sounds incredibly complex. You're bending time to make the data fit.
You are, and if you get it wrong, the whole system feels uncanny or just breaks.
Moving on to challenge number 3, reasoning. This is where we stop just seeing and start thinking.
Reasoning is defined as composing knowledge, usually through multiple steps. It's not just pattern matching anymore, it's logic.
The paper brings up knowledge graphs here.
And this is crucial. To reason, an AI often needs to know things that aren't in the data. Let's say an AI sees a picture of a broken vase on the floor and a dog looking guilty nearby.
Classic scenario.
The image doesn't show the dog breaking the vase. To understand what happened, the AI needs to access a knowledge graph, basically a database of common sense that says dogs run, vases are fragile, and impact causes breakage. It combines the visual evidence with that external knowledge to infer the sequence of events.
So reasoning is about filling in the blanks using logic.
Exactly. It's what allows the AI to say the dog probably do it, rather than just there's a dog and shards of glass.
Challenge number 4 is the one everyone sees in their newsfeed. Generation.
The creative side, yeah. This involves learning a process to produce raw modalities from scratch.
Like when I type astronaut riding a horse on Mars, and it spits out a photorealistic image.
That's translation, moving from text to image. But the paper points out it's harder than it looks. You have to maintain content consistency. If you say the horse is white and the AI generates a brown horse, it failed the generation challenge.
They also mention creation as distinct from translation.
Creation is the heavy lifting, generating multiple modalities at once. Think about generating a virtual avatar. You have to generate the video of the face moving and the audio of the voice and make sure the lips sync with the sound. If that coherence slips even a tiny bit, the illusion is ruined.
It's like being the director, the actor, and the sound engineer all at once.
In real time.
Challenge Jordan there.
Number 5 is one that I hadn't really thought about before, but it seems incredibly useful. Transference.
This is the helper function. It's a clever way to solve the problem of data scarcity. Because we don't have equal amounts of data for everything, right? We have the entire internet of text, but maybe not much data on underwater basket weaving, tactile sensations.
Exactly. So transference is about using a resource-rich modality to help train a resource-poor one.
How does that work in practice?
Let's look at robotics. We want robots to be able to identify surfaces by touch. Is this smooth, rough, slippery? But gathering millions of hours of touch data is really, really hard.
You'd have to have a robot just poking things for years.
For years. But we have millions of hours of video.
Bingo.
We have endless video of surfaces. So through a process they call co-learning, we can use the visual representations of roughness, what sandpaper looks like, to help structure the model for what sandpaper feels like.
So you're using the eyes to teach the hands.
It's almost poetic. The strong sense guides the weak sense. It implies that knowledge isn't locked to a specific sense, it's shared.
That ties back to those connections we talked about earlier.
Yeah.
Finally, challenge number 6, quantification. This sounds like the report card.
It's the reality check, and honestly, it's the area that needs the most work. Quantification is all about empirical studies, measuring how well the model is actually learning.
Why is this a challenge? Can't you just see if it got the answer right?
Not really, because of the black box problem.
Yeah.
If the AI correctly identifies the sarcastic face, is it doing it because it truly understands the interaction between the text and image? Or did it just get lucky? Or did it just memorize a specific pattern of pixels?
So quantification is about digging in and checking the math.
It involves measuring things like the signal-to-noise ratio or checking for bias. If your data set has mostly pictures of sunny days, your multimodal model might fail terribly when it hears the sound of rain because it hasn't quantified that heterogeneity correctly.
It's the difference between a hacky demo and a robust scientific system.
Exactly. And that really sums up why this paper is so vital. It's trying to build a scientific foundation for a field that is moving at breakneck speed.
It stops us from just throwing spaghetti at the wall to see what sticks.
Right. By identifying these 6 challenges, the authors are giving researchers a common language. Instead of just saying, my model works, you can now say, my model solves the alignment challenge using this new warping technique. It allows for collaboration and real progress.
And it also highlights the gaps. I mean, the paper makes it pretty clear we haven't solved all this yet.
Oh, far from it. The authors specifically point out long-range dependencies. We are still pretty bad at teaching machines to remember a connection between a visual cue at the start of a movie and a line of dialogue at the very end. The alignment just breaks down over time.
And that noise heterogeneity is still a beast.
Yes, when the noise in the audio doesn't match the noise in the video, current models get very, very confused. So there is plenty of work left to do.
But the destination, truly perceptive AI, seems worth the effort.
Absolutely. Moving from simple classification to true understanding and reasoning.
So zooming out, we have these 3 principles describing the nature of the data: heterogeneity, connections, and interactions. And we have the 6 challenges to build the systems: representation, alignment, reasoning, generation, transference, and quantification.
That's the framework.
Why does this matter to the person listening right now? Why should they care about fission or alignment?
Because this isn't just academic theory anymore. This is the operating system of the future. We're moving out of the phase where AI is just a cool parlor trick. We're integrating these systems into cars, hospitals, and our phones.
It's happening in our pockets right now.
Exactly. So next time you use a generative AI tool or you see a robot navigating a warehouse, realize that underneath that smooth exterior, there is this massive struggle going on to align and fuse these radically different types of mathematics.
It gives you a new appreciation for the technology. It's a minor miracle that these machines can make sense of our messy, noisy, chaotic reality at all.
It really is. And I leave you with one final thought on that transference idea, which I think is the most provocative part of the paper.
Oh, if machines can transfer knowledge from text to vision or from sound to touch, if the strong sense can teach the weak sense, does that imply a form of synesthesia for AI?
Synesthesia, like seeing colors when you hear music.
Exactly. If the mathematical representation is shared through these tensors and connections, could an AI eventually see a sound better than it hears it? Could it understand the texture of a velvet couch primarily by listening to a description of it?
That is a trippy thought. A machine that sees music. I'm going to be thinking about that one for a while.
It's theoretically possible within this framework. The boundaries between the senses are much more fluid for a machine than they are for us.
We'll leave it there. Thanks for joining us on this deep dive into the foundations of multimodal learning. We'll see you in the next one.